of classes, the lecture slides, you have not uploaded them. So could you please upload them on the
Yeah, I'll do
Teams?
it. Yeah, that is on my list of things to do. Is my screen visible?
Yes.
Okay. Let me know if there is a lag, so I will slow down. Okay. So today's lecture, we're gonna cover stable isotope geochemistry, or essentially isotope geochemistry from the perspective of stable isotopes. It's gotten a bit hodgepodge. Next lecture, we're going to do a bit of reading on why do we have these isotopes. Like essentially, the question is, why is there a lot of hydrogen around? Because it's the material we started with. Now, if you look at anything heavier than hydrogen, their abundance is not uniform. There's a lot of iron around, there's a lot of silica around, and the question becomes, why do we have particular elements at a much higher abundance than other elements? So that will be part of the next lecture, which was supposed to be this lecture, but unfortunately I left all the slides home. So I have to jump onto the stable isotope part and then go back to that part. Okay. Now, what do I mean by stable isotope geochemistry? By stable isotopes, I mean isotopes or elements which are not decaying with time. Okay, so they're not radioactive. You can also apply it to radioactive elements if they have a very, very long half-life. So if a particular element has a hundreds of million years to a billion-year half-life, you can apply the principles of stable isotope geochemistry to that particular isotopic system for processes which are happening over 1,000 years to 100 years time scale, because over that time period, the radioactive element is not going to decay by a significant amount. So stable isotope geochemistry has a very strong application in terms of environmental tracer. We can fingerprint sources, we can fingerprint sinks. It's extensively used in archaeology to talk about what was the diet like, where people migrated from, because at the end of the day, you are what you eat. So what I'm going to do in this lecture is I'm going to take you through the principles of stable isotope geochemistry and then discuss a bit about what sort of fractionation we observe in nature, especially in plants, and how that signature can be incorporated into human body or animal body, so that we can kind of investigate where the animal came from, where it's going, and stuff like that. Okay. A quick overview. What we're going to deal with are isotopes. A stands for mass number, Z for atomic number. I don't need to bother about that. What are isotopes? Essentially, they have same number of protons but different number of neutrons. A good example is carbon-12, carbon-13, and carbon-14. Though carbon-14 is radioactive, it has a half-life of 5,732 years old. If you're observing a process which is happening over days, all these isotopes are going to behave like stable isotopes. If you're observing a process which is happening over thousands of years, 14C is not going to behave in the way a stable isotope should behave, because its composition is going to be a function of both isotopic fractionation and radioactive decay. And the question becomes, why do we bother ourselves with stable isotope geochemistry? Firstly, it can be utilized as a climate proxy, and then it is also a biogeochemical tracer. More recently, it has been strongly utilized as a pollution tracer. Like, you might be dumping heavy metals into river, and you might argue that this is natural. This is not an artificial thing. But looking at the isotopic signature, we can definitely tell that whether it's anthropogenic or natural. Okay. Now let's look at the chart of nuclide first. What we have here is the number of protons going up from 0 to 17. 0 proton, you're essentially a neutron. All the isotopes of the elements marked in blue are the stable ones. Okay. Now anything that, hang on, let me get everything on this slide. Okay. Because thought this. Okay. What are isotopes? Isotopes are anything that falls along a row. So we have the same number of protons, different number of neutrons. What are isobars? That it's a diagonal relationship. You have the same number of protons plus neutrons, but the number of proton is changing. So you're jumping from one element to the other, but your total mass number is remaining constant. Okay. The elements which are marked in gray are the cosmogenic radioactive isotopes like 10 beryllium, C14, okay, aluminium 26. Tritium, as we know, is a radioactive stable isotope. Okay. Now, the Odo-Haken rule says that if A is an even number, then it's more stable. And we're going to discuss that in next lecture. Why is the even number systematics is more stable? If we go through the periodic table and look at the Z and the N values, what we see is that the even abundance is the maximum and the odd abundance is one of the lowest. 6 lithium, 10 boron are giving you some of the classical odd abundances. Okay. Now, the symmetry rule dictates that for Z values less than 20, an N by Z ratio of 1 leads to a stable isotope. So the slope of the line up to mass 20 remains around 1. Beyond mass 20, the N by Z ratio has to be 1.5. Essentially, to pack that many number of protons into the nucleus, you need more and more neutrons to buffer the system. Okay. Now, what do I mean by isotopic fractionation? All through high school and all, you have read that two isotopes behave exactly the same way in a chemical reaction or a physical reaction. But no, they don't. As soon as there is a mass difference between two isotopes, there has to be a difference in the rate of their chemical reaction or physical reaction. Why? Because the bond energy associated with a heavier isotope is more. The kinetic energy of a system, in a gaseous system, we know is a function of temperature. But if the two isotopes of different masses have the same kinetic energy, then the lighter isotope must have a higher velocity. So it will be closer to escape velocity. So in a process like diffusion, it will escape the system faster. Okay. Now, in terms of fractionation, what we mean is that it's a change in isotope ratio during any physical or chemical transformation. Without a physical or chemical transformation, there cannot be any fractionation. So there has to be a change in the composition. There has to be a change from one reservoir to the other. Simple evaporation, simple precipitation is a good enough process, a physical process, to cause fractionation. Okay? Precipitation causes a large amount of fractionation. And there are two types of, generally, we call two types of fractionation in nature. Equilibrium fractionation happens under steady state conditions. For equilibrium fractionation, we need chemical equilibrium or physical equilibrium to be there. For kinetic fractionation, a good example of equilibrium fractionation is that if you have a bottle with some headspace tightly capped, the air in that headspace is going to be in equilibrium with the water. Now, if you change temperature, the direction will move. So whenever we talk about equilibrium fractionation, we have to say that this is at for this temperature and this pressure. Okay, so the physical parameters, like every chemical reaction, needs to be specified. And the interesting bit is the kinetic fractionation. Kinetic fractionation happens for unidirectional or incomplete processes. Precipitation reaction, okay, is a good place where we have kinetic fractionation. And all biological system kind of loves kinetic fractionation because most biological processes are fast. Okay. So we're going to go there. Let's start with an example of equilibrium fractionation. This is calcium carbonate. Say a piece of calcium carbonate is sitting in water, and it's a saturated solution. Just because it's a saturated solution, it doesn't mean that calcium carbonate is not dissolving. It's dissolving and reprecipitating at an equal rate. So the net change in the amount of solidus, the amount of calcium carbonate in the solid phase, or the calcium concentration and the carbonate concentration in the solution are not changing. What happens in a situation like that is that the O18 from the water molecule is going to jump to calcium carbonate molecule. And why is that happening? We are in a liquid and this is a solid. This is a heavier isotope. So a heavier isotope, once it gets into the solid phase, that bond is difficult to break. So the back reaction is much slower than the forward reaction. So that way there is a preferential, I would say, accumulation of the heavier isotope in the more stable phase. So this is the cardinal rule of isotope fractionation. There is always a preferential accumulation of the heavy isotope in the more stable phase. So if you move from vapor to liquid and liquid to solid, what you will see is that the heavy isotope preferentially goes from vapor to liquid and then from liquid to solid. And this is what we are observing here. Okay? And this can be expressed as the concentration of each of the species in the system, just like the chemical equilibrium. And that is given by the fractionation factor. Okay. Now, the question becomes, why do isotopes fractionate? So we are looking at an energy potential well. Okay. And on this side, we have interatomic distances. We are considering three different molecules of hydrogen and deuterium combination, H2, Hd, and D2. This line denotes my 0-point energy. And we know that the 0-point energy of deuterium is lower than the deuterium hydrogen and the hydrogen. What, for this particular system to participate in any chemical reaction, we have to break these bonds. To break these bonds, we have to supply them with a particular amount of energy. The deeper in the well that you sit, the more energy you require to become reactive. Heavier isotopes are sitting deeper in the well, because the frequency of oscillation is a function of the reduced mass, and the K here stands for the bond strength, and we know that the bond strength per se is a function of mostly difference in electronegativity. Okay, so following that principle, we can definitely say that the deuterium bond is far more difficult to break than the hydrogen bond. So if any reaction needs to happen, the deuterium will be less inclined to participate in it than the hydrogen. Okay? Keep that in mind. Now, when we deal with isotopes, we need to be cognizant of the isotopic nomenclature. R usually stands for the number of atoms of the heavy isotope divided by the number of atoms of the light isotopes, known as isotope ratio. When we express the isotope ratio as a del sign, the del is nothing but R sample minus R standard divided by R standard times 1000. Instead of 100, for percentage, we are multiplying by 1000. That's why we call it per mil. Why do we multiply by 1000? Because the ratios change by such a small amount. To get a realistic number, whole number, we need to multiply it by 1000. Okay. For example, delta 18 of calcium carbonate is given as 18 to 16 oxygen ratio in calcium carbonate to 18 to 16 oxygen ratio in SMO minus 1 times 1000. SMO here stands for standard mean ocean water. So for every isotope isotopic composition that's been reported, you need to know what is the standard with respect to it's been reported. Okay. That's about it. Now, different systematics have different isotopic standards. What is a standard? In isotope space, a standard is something which is homogeneous in isotopic composition and available in large quantities. As simple as that. Homogeneous in composition, available in large quantities. If I took a bucket of water from Bay of Bengal, surface Bay of Bengal, it is not small. Why is it not small? Firstly, I have a lot of river discharge. So there is a lot of fresh water coming into the surface Bay of Bengal. It's not pure seawater. Also, there is evaporation and precipitation happening at the surface of the ocean. So that is changing the isotope ratio because we know every physical process imparts a fractionation to the reservoir. Which means to get a small sample, I have to go deeper in the water column, somewhere like a kilometer depth, where the water is not impacted by the surface processes, be that river discharge, be that precipitation, be that evaporation. So for oxygen and hydrogen, we can use the standard mean ocean water as our standard. Then comes carbon, for which we use a belemnite. This is essentially a calcium carbonate, biological precipitate of calcium carbonate, which is very pure. Nitrogen, the atmosphere. And for sulfur, we use a particular meteorite known as Canyon Diablo troilite. Okay, and that is how we deal with it. Couple of things to remember. Delta is the deviation from a standard ratio. Okay. And it's always expressed with respect to a standard, and you have to specify the standard. And the delta value of a standard is 0, as expected. Okay. The dominant, there is one isotope which is dominant in the abundance and is known as the common isotope. And the one that is less abundant is known as the rare isotope. And when we say that a particular sample has a delta value greater than 0, we imply that it's enriched in heavy isotope. When the delta value is less than 0, it's depleted in heavy isotope. We don't say it's enriched in light isotope per se. Okay, we avoid saying that. So the nomenclature dictates that delta greater than 1, greater than 0 means it's enriched in heavy isotope. Less than 0 means it's enriched in, depleted in heavy isotopes. A good example is when we form sea ice. Essentially, when we freeze seawater at -2 degrees Celsius, the ice that is formed has a delta 18O value higher than the mean seawater from which it's forming. So it's usually around 6 per mil heavier. The ice is 6 per mil heavier than the seawater from which it has formed. Okay. Now, for every systematics, for every physical process or every chemical process, there is a fractionation associated with it. And that fractionation is quantified by the fractionation factor. Fractionation factor, very simply, is defined as the ratio in phase A of a particular pair of isotopes to the ratio in phase B. For example, for 18O, in the calcium carbonate water system, the alpha value of calcium carbonate water is the 18O to 16O in calcium carbonate and 18O to 16O in water. Okay. And please remember, these fractionation factors are a strong function of temperature. Okay. And we're going to cover that later. How that is changes with temperature, it usually follows an exponential function with temperature. Lower that, and note the temperature given here is in Kelvin scale. Lower the temperature, higher the fractionation. Higher the temperature, lower the fractionation. That is the cardinal rule of it. Now, alpha can be expressed as this. There is no need to go into excruciating details of it. But one simple principle, for temperature greater than 500 degrees Celsius, 1000 in alpha is 8 × 10⁶ by T squared, T is in Kelvin. And for temperature less than 500 degrees Celsius, 1000 in alpha equals to 8 × 10⁶ T squared plus B. Okay. Above a particular temperature, we see this sort of relationship. Below a particular temperature, we see this sort of relationship. Now, if we have the delta value for an AB system versus an BC system, delta AC can be calculated using the following formula. We don't simply add the two delta values. It follows this particular formula. Now, we often use the term enrichment factor. Enrichment factor is nothing but the change in isotopic composition between phase A and B. The enrichment factor cap delta or big delta is alpha minus 1 times 1000. And for a difference in del values of very small, less than 10 per mil, we can say cap delta is 1000 in alpha. Now the question becomes, why are we so interested in stable isotopes, light stable isotopes? Firstly, light stable isotopes with a low atomic mass usually have a large relative mass difference between the isotopes. For example, between hydrogen and deuterium, the mass difference is 100%. So we observe extreme amount of fractionation. What we have here is the delta deuterium value going from plus 50 per mil, 0, to minus 200 per mil. As expected, seawater is sitting at 0. Standard means ocean water will be exactly 0. However, if we take all the seawaters that has been measured in the world, it will follow a little bubble over here. Why? Because certain seawaters are enriched due to evaporation. Evaporation will take away the lighter isotope preferentially, leaving the heavier isotope behind. And certain seawaters are depleted because of rainfall or river discharge. You can see that the rainfall has a large range. Geothermal water has a large range. Okay. And all other reservoirs of hydrogen has quite a significant range associated with it. The other bits about light stable isotope is that they form highly covalent bonds. And the stronger the bond, the more fractionation we can expect. Elements that exist in multiple oxidation states, as you skip from one oxidation to the other, there will be isotope fractionation associated with it. So a lot of chemical reactions, redox reaction, can be traced using isotopic composition. And they are sufficiently abundant. So anything that you want to apply needs to be measured precisely. Without large enough abundance, you can't measure it. Okay. Mass-dependent fractionation is something that follows simple mass-dependent rules. For example, the relative mass difference between hydrogen and deuterium is 1. Oxygen 16 and 17 is 1 by 16. Oxygen 16 and 18 is 1 by 8. So for a process in which I am taking liquid water and vaporizing it, the delta deuterium of the vapor will be 8 times larger than the delta deuterium of the delta 18O of the vapor. So deuterium to the 18O relationship is 1:8. So every time I say that the delta 18O of a water is 1 per mil, you can safely say the delta deuterium of that water will be 8 per mil, because they will always follow mass-dependent fractionation. Similarly, the delta 17O of vapor will be half that of delta 18O of the vapor, okay? Because the mass difference is 1 by 16 versus 2 by 16. Now, equilibrium fractionation in that way follows a few rules. It's temperature dependent. Ln alpha is proportional to 1 by t square. The degree of fractionation is proportional to mass difference. Okay. And the heavy isotopes always prefers the stable phase. Be that higher oxidation state, stronger bond, lower coordination number, and low spin electronic configuration. Everything and anything which leads to a stability of the particular compound will be preferred by the heavy isotope. As we observed in the first example we started with, 18O from water is skipping to calcium carbonate and sitting in calcium carbonate. Okay, this is the enrichment of the solid phase compared to the liquid phase. Now, kinetic fractionation. Kinetic fractionation is mass dependent in nature, as associated with anything that happens rapidly. It doesn't go to completion, and usually all unidirectional processes are associated with kinetic fractionation. It's very dominant in biological systems. Now, for a given pressure and temperature, let's take a gaseous system. If we fix the P and T, we know the kinetic energy equals to 3 by 2 kT. Okay, so the kinetic energy for a the carbon dioxide in the atmosphere for the 13C16O2 molecule and the 12C16O2 molecule are the same. And that can be expressed as a function of their mass and velocity. And if we take the mass and velocity and arrange the equations like this, what we observe that the velocity ratio of 12C16O2 and the 13C16O2 is root 45 by 44. That's 1.001. So which essentially means the distance covered by 12C16O2 is kind of 1.0011 times higher than the distance covered by the 13C16O2. Make a note of this. This will become important in the later sections. Kinetic fractionation usually follows Rayleigh fractionation. Rayleigh fractionation happens wherever there is a distillation process or wherever there is a precipitation process. What happens is that on this axis, we have the isotopic composition of the, say, you're transforming from liquid to vapor. You have the isotopic composition of the vapor. If it followed equilibrium fractionation, this would be the line it followed. How can we give an example of a liquid to vapor in an equilibrium system? You have a saucepan with water on it, with a lid on a stove. If you keep it at a particular temperature, there is vaporization, there is condensation. So that is an equilibrium system. Beyond a certain point, there is some amount of water in the vapor phase, but you're constantly putting water in the vapor phase and you're taking out water from the vapor phase through condensation to the liquid phase at the same rate. So that is equilibrium fractionation. However, Rayleigh fractionation means an open system where you are rapidly evaporating that water. So the isotopic composition of the water, the vapor, will initially change like this. Okay? A good example in nature is that rainfall. What happens is that when you form clouds from the ocean, the lighter isotope preferentially escapes and forms the cloud. So the vapor that you form has an isotopic composition of around -13 per mil. If the delta 18O value is -13 per mil, what will be my delta T value? It will be 8 times -13 per mil. Now, when precipitation happens, it's the reverse reaction. The heavier isotope will preferentially go into the liquid phase from the vapor phase, which means the rainfall is isotopically heavier than the cloud. Now, any physical or chemical process, we are not creating isotopes. The number of isotopes are constant to start with and should be constant in the end. All we are doing, we are partitioning them between different reservoirs. So if the rainfall preferentially takes out the heavier isotope, the remaining cloud will be further depleted in the heavier isotope and will become isotopically lighter. So what happens as we move away from the source of the moisture, every rainfall becomes progressively isotopically lighter, even though there is an equilibrium fractionation between the cloud and the rainfall, and which we can say that it's happening at a particular altitude in the atmosphere at a constant temperature. And as long as the mass fraction being converted from the vapor phase to liquid phase remains constant, this fractionation will not change. But since you're constantly stripping the system of the heavy isotope, whatever is left behind is becoming isotopically lighter with time and as you move towards the center of the continent. A good example is the global precipitation line. What we are looking at here is delta 18O of the mean precipitation water and the delta deuterium of the precipitation water in small scale. This is the 0-0 axis. This is small. And then we are moving away from the coastline. We are starting with Bombay, going up to Delhi, somewhere like Chicago, Goose Bay, Edmonton, and we are not only that, we are also moving northwards. And what we can see is that as we move away from the equator, isotopic composition of the rainfall is becoming lighter and lighter because of radial distillation. Now, this brings us to the systematics where we look at isotope fractionation in plants. Biology wants to spend as little energy as possible in creating food for itself. So we observe that it takes more energy to break the bond which involves heavier isotope. So all biological processes will have a preference for the lighter isotopes because it's much easier to break those bonds. This is an overview of what we observe in nature. The atmospheric delta 13C value is -7 per mil. And it's dominantly controlled by the degassing of the mantle. Mantle itself is sitting at -7 per mil. So atmospheric composition is controlled purely through mantle processes. Now, plants that live and grow in equilibrium with atmospheric CO2 will have their distinct isotopic signature. C3 plants have an average isotopic signature of -27 per mil, and C4 plants have an average isotopic signature of -13 per mil. And then there are the CAM plants like cactus and agavetti, okay, at 9, which have a very different isotopic signature. C3 are our trees, shrubs, cool season grasses. C4 are our grasses, which includes corn, sugarcane, millets, and other things. Okay, this will become important. Why? Because this will help us understand how we can use isotopes to assess the purity of honey, purity of alcohol, because honey has to be sourced purely from C3 plants. It has to come from flowers of trees. If you add corn syrup to your honey, you're adding a C4-based product to a C3-based product. C3 product should have a range of -35 to -20 per mil. C4 will have a range of -9 to 17 per mil with an average of -13 per mil. So you add any amount of C4 to C3, you will change the isotopic composition, and one should be able to track it. So how do carbon isotope fractionation happens in plants? Let's take an example of C3 plants, which dominates the terrestrial and the marine systems. Okay, we are starting with a process which leads to the diffusion of CO2 through stomata into the internal airspace of the plant. And this diffusion of CO2 leads to a kinetic fractionation. Why? Because 12 CO2s can diffuse faster than the 13 CO2 molecules. And the carbon's fixation process leads to another set of fractionation through Calvin cycle. For terrestrial plants, it's -30 per mil, and for bacterial processes around -20 per mil. Now, this can be expressed as a formula like this. Delta 13C of a plant is equal to that of atmosphere minus A, which is the fractionation caused by diffusion, and minus B minus A by Pi by Pa, which is essentially the ratio of intercellular CO2 concentration to atmospheric CO2 concentration. So this is the gradient of CO2 diffusing into the cell. Now, the enrichment factor for this case can be expressed as A plus B minus A by minus Pi by P. Okay. For a very high enrichment factor, we have a very light isotopic composition of the plant. And as this ratio increases, the enrichment factor, or the delta 13C of the plant, becomes more and more lighter. Now, why do diffusion causes of fractionations? From simple Fick's law, flux is minus d dc dz, where d is the diffusion coefficient. The diffusion coefficient for a one-component system can be expressed as this, root over m2 by m1. And for a multi-component system, it's root over mu2 by mu1. And mu stands for the reduced mass. And following that particular principle, what we can say is that in comparing 12 CO2 versus 13 CO2, 12 CO2 has a much higher velocity than 13 CO2. So simple diffusion processes can impart a fractionation of around 11 per mil if it's allowed to go to completion. What we observe in atmosphere is this, that if there is a fractionation factor of around 1.004 for 12C versus 13C, and that causes a fractionation of around 4 per mil during the diffusion from the atmosphere through the stomata. On the other hand, we have the C4 plants. C4 plants have the same diffusion-driven fractionation happening during the CO2 uptake. Okay. Now keep in mind, stomatal diffusion is a function of the aperture of the stomata. The larger the aperture, faster the diffusion. Smaller the aperture, slower the diffusion. Faster rates of diffusion versus slower rates of diffusion will have different fractionation factors. Now, once the CO2 is inside the tree in a C4 plant, it goes a multi-stage process, the bundled sheet Rubisco. Okay. Now, this happens in hot water stress and low atmospheric CO2 concentration. That's where C4 plants dominate. Okay. And this can be expressed as the following equation, as the Hertzsprung cycle, where delta 13C of the plant is that of C of atmosphere minus A, which is the diffusion driven. Then comes the B4 term, which is caused by the PEP carboxylase cycle, then caused by the Rubisco fixation. And then there is our PI minus by PA term, which is the atmospheric CO2 concentration to intercellular CO2 concentration ratio. Keeping in mind, we can express this as this. So again, as PI by PA increases, cap delta decreases. How does water stress dictate delta 13C? When we have low water stress, you can have larger stomatal opening, because even if you lose a bit of water, if the plant loses a bit of water, it's not worried about it. Which means there is a larger PI by PA ratio, and we can have more depleted delta 13C. When you have low water stress, we have much smaller stomatal opening. We have much smaller PI by PA. We have less depleted delta 13C. CAM plants are similar to C4 plants, mostly found in very dry conditions. The obligate plants, which are like C4, and the facultative CAM, which has a ratio of minus 20 to 10 per mil. We are not much interested in this section. Now keep in mind, the delta 13C of a plant can change as a function of photosynthesis rate. Okay, if the rate of photosynthesis is plotted against intracellular CO2 concentration, we observe that for C3 plants, the plateau never happens. It happens at a much higher intercellular CO2 concentration. Whereas for C4 plants, it happens at a much lower CO2 concentration. So C4 plants are optimized for operation in low CO2 concentration. A classical example of this comes from the marine carbon profile. Remember, the total CO2 or DIC profile of seawater looks like this. In the surface ocean, there is depletion due to photosynthesis. And in the deep ocean, there is almost constant DIC value. The depletion of CO2, the total CO2 or DIC due to photosynthesis, is through uptake of CO2 for biological processes. Now we know biology will preferentially take up the lighter isotope, leaving behind the heavier isotope because it requires less energy to mobilize the lighter isotope. As a result, if we plot the delta 13C of the seawater DIC, so we are plotting the DIC delta 13C. In the surface ocean, the delta 13C will be isotopically heavier because the lighter isotope has preferentially gone into the organic matter, leaving the heavier isotope behind. Thus, there is a large, heavy signature we observe in the surface ocean. And as we get deeper and deeper, we find this slight bulge over here, which is dominantly due to respiration. And then there is a standard curve. So wherever there is biology, there is a strong signal on the isotopic signature. Now, delta 13C of methane is also a very powerful tracer. It depends on the production mechanism. Any biogenic methane has a composition of around -50 per mil or slightly less than that. Okay. Thermocatalytic methane has a signature of higher than -40 per mil. And mantle methane has a signature higher than -50 per mil. So if you find methane somewhere, you can use purely the isotopic signature to say whether it's biogenic, whether it's thermocatalytic, or whether it's a biogenic or coming from the mantle. So this is source fingerprinting of your tracer. Now, nitrogen isotopes we have heard about a bit in terms of trophic level migration. As you go up the trophic level, more and more lighter isotopic composition that we will expect. Okay. So if we take this information and the carbon information and put it in one cross plot, we can carbon isotopic composition in ppb scale over here and delta 15 nitrogen in atmospheric scale over here. We can compartmentalize different plants and different biota in different sections. For example, here lies our C3 plants, which are carbon isotopically very light, okay, and pretty heavy in terms of nitrogen isotopes. Here is our C4 plants, which are isotopically distinctly different from the C3 plants. Here are the legumes, which are C3 plants, but they are getting their nitrogen isotope directly from the atmosphere. So their nitrogen isotopic composition is close to 0 per mil. And then there is the marine cyanobacteria, which are also getting their carbon isotope, nitrogen isotopes from the atmosphere, but has close to a large range in carbon isotopic composition, because depending what the DIC carbon isotopic composition is, they're going to have their own intrinsic carbon isotopic composition. We can make it a bit more complicated. We can look at different types of populations where they fall in the C3 versus C4 grid. From that, like we can see, the Neanderthals are falling close to the C3 plant grid, so they are mostly surviving on products from trees. They have not gotten into agriculture because this will be our grassy agricultural systematics, okay? And any particular biota will have its own signature 13C delta 15 nitrogen composition. And by putting it in the grid of 13C versus 15 nitrogen, we can say what its diet is, what its habitat is. Okay? This is essentially coming from the fact that we are what we eat. As we go up the trophic level, we have a heavier and heavier nitrogen isotopic composition. As we go up the trophic level, okay, we have a heavier and heavier carbon isotopic composition. However, the source carbon and the source nitrogen are fixed by primary producers. Okay, so this is where we can use carbon isotopes both in biology, archaeology, and pollution systematics. Do we have any questions? Any question with any of the topics? Oops. I hope I'm still audible. You guys have not all fallen asleep. Yeah. Go ahead. Yeah.
This is actually a question I had from a few lectures back. I think I just never got around to asking it.
Sure.
In the salinity map, most of the major river mouths had like low salinity, but Mediterranean in general had very high salinity. There's no decrease in salinity close to the Nile.
No.
Why is that?
Firstly, Nile doesn't carry a lot of water. Nile, it might be the longest river, but it's not a large river in terms of water flux. You can imagine it's flowing through a system which is exceptionally arid. So there is not a lot of precipitation. It's only the headwaters which is sustaining it. And the Mediterranean itself is lying in a strongly evaporative region. So its salinity is much higher than any other ocean. Does that answer your question?
Yeah, that clears things up. Thank
Sure.
you.
Anybody else? Okay, we'll end here. Even if there is a, what do you call it? Assignment, you are expected to turn it in. If you don't, I will probably not dock any marks. Okay, so don't worry about it. And next class probably will be our last class, and by that time I'll talk to Prosenjit and get a overview of what he wants to put in his part of the syllabus. Okay, anything else I need to be aware of? Okay, folks, thank you. I'll see you next class. Bye-bye.
Thank you, sir.